So let us go back to our discussion of the Stern-Gerlach experiment. The Stern-Gerlach experiment, as I told you, measures some component of the intrinsic angular momentum of the electron, and here we have a situation where we have a Stern-Gerlach experiment aligned along the z-axis. So it measures the z component of the intrinsic angular momentum or the spin of the electron. And we found that the answer comes out to have two possibilities only. The result of such a measurement comes out to have only two possibilities, plus half h cross or minus half h cross. This was the first very interesting feature, that the intrinsic angular momentum has only two possible values, half h cross and minus half h cross. The second very interesting feature which we saw was that suppose we have an unpolarized atom coming in and we send them through a Stern-Gerlach apparatus aligned along the z-axis. The atoms get split up into two beams, one corresponding to the situation where the particle's electron spin is up, which is the one on top, and the other corresponding to the situation where the electron spin is down. These are the only two possibilities, and two beams come out of the apparatus. Now if we stop this beam and only retain the particles which have spin up along the z-axis, and then make a measurement of the x component of the spin, we find that in the process we have again reintroduced some spin along the minus z direction, which we had wiped out, which we had removed from these particles which had the spin down had been removed earlier, but a measurement of the spin component along the x-axis we found again introduces this minus component of the spin along the z-axis. This was another very interesting feature which we saw. And we also saw that polarization of light has an exactly analogous behavior. So if we have light traveling in the z direction, the electric field is polarized in this xy plane. Now if we send the light in through a polarizer which polarizes it in the x direction, all polarization component along the y direction has been removed. This is x, this is y. The light is traveling this way, and after the light travels through a polarizer in the x direction, all y component of the polarization is removed. Now if this light is next sent through a polarizer at 45 degrees, this reintroduces some component of polarization along the y direction. And this is, we saw, exactly analogous to the situation with the spins of these particles, where a measurement along the x-axis reintroduces the spin down component along the z direction. So now let us try to develop some mathematics for modeling this situation, and we shall proceed to develop this mathematics to describe the behavior of the spin of these electrons in exact analogy with the polarization, the mathematical description of the polarization. So, so the polarization state of light polarized light propagating along the z-axis can be expressed as a linear superposition of these two vectors, that is, the electric field oscillating along the x-axis and the electric field oscillating along the y-axis. This represents the situation when the electric field is along the x-axis, and this is the situation where the electric field is along the y-axis. We can superpose any of these, we can have any linear superposition of these two and produce some other linear polarization state. So in what follows, I shall not show this exponential part, phase part, because it is going to be common throughout. So I am not going to show these two, I am only going to write this and this part. You can assume that this is going to be there throughout. Okay, I shall not put this explicitly all the time. So the the polarization state over here is Ex not I now the polarization state corresponding to this, the second one is E naught Ex naught I plus E y naught j, this whole thing, by 1 by square root of 2. And I am assuming that these two amplitudes are the same. Now so this represents a unit, the polarization state along the x-axis. Here these two amplitudes are the same. So this superposition represents a electromagnetic wave polarized along 45 degrees. And this is E y naught j. So what is the mathematical description of these three measurements? So after I make this measurement, the electromagnetic wave which comes out will have some amplitude which I am not writing explicitly into this thing over here. Now when this is incident onto this polarizer, the component of this, so this is a vector and this is a vector, the component of this vector in this direction is what will come out. So there will be some overall amplitude, and the resulting vector, electric vector field which comes out here will be given by this. This is a electromagnetic field oscillating in the 45 degree axis, because these two are same, and I have given this 1 by square root of 2 for overall normalization. There will be some overall amplitude which will be less than this amplitude over here. So this is the resultant of this polarization measurement. So initially I have no y component of the electric field. The y component has been totally wiped out after this. Once I make a measurement of the polarization along the 45 degree axis, the polarization state is given by this vector into some amplitude. So now we see that the y component has been reintroduced. Now if I make a measurement of the polarization, I find that I have got both the x and y component again, and I get a finite y component. The y component of this polarization state can also be worked out by taking the dot product of these two vectors. That will be the amplitude, and this is the direction. This represents the direction. So we see that the mathematical description of the intermediate polarization states, or all possible polarization states, can be expressed by linear superpositions of these two electric fields along any two principal directions. And here the principal directions have been chosen as this x and y axis. Any other polarization state can be described by a linear superposition of these two vectors, Ex and Ey. So the 45, so let me again write them down systematically. So we have the two unit principal directions which we have chosen are the polarizations along the x-axis, which we can say is some E naught, I will forget about the E naught x, so E naught into I, and polarization along the y-axis, which is E naught into J. Then we can have the electric field polarized at 45 degrees. So this is one situation. And these we see are two orthogonal situations, in the sense that if the light is polarized along the x-axis and I make a measurement of the y component, then I will get absolutely nothing, which is the situation I have shown here. If you remember, I send the light through a polarizer along the x-axis. Now if I make a measurement of the y component of the polarization, I will get absolutely nothing coming out. Similarly, if I send the light along the through a y polarizer, and if I send the output through a x polarizer, I will get absolutely nothing coming out. So these two states are two orthogonal, you may think of them as two orthogonal states, and the equivalent states which you might guess for the spin of the particle are when the particle has got spin up or spin down along some fixed direction. So if I send the particle through a Stern-Gerlach experiment and I find that it is the analogous situation for the Stern-Gerlach experiment, let me also put that here. The analogous situation for the Stern-Gerlach experiment, if I, let us say I get Stern-Gerlach Z and I block out the particles with spin down and I send this through another Stern-Gerlach apparatus, I will find that nothing comes out over here, only this comes out, nothing comes out over here, nothing, right. Similarly, if I block out this one and send this into the same Stern-Gerlach, similar Stern-Gerlach apparatus, so I have blocked out all the particles with spin up and I am only allowing the particles with spin down to go through, then again I will find that there is nothing with spin up coming out here, only particles with spin down come out. So the analogous situation we can see for the spin of the particle along the z-axis are the two states with particle spin up or with particle with spin down. So let me also denote the states of the corresponding state of the spin of the particle. So let us denote that by plus and minus z. So this is z, okay, so along the z-axis. So plus, let me change the notation. So this is going to be denoted by Sz plus and Sz minus. So in optics, I have two polarization states, one with the electric field polarized along the x-axis, when the light is linearly polarized along the x-axis, another where the light is linearly polarized along the y-axis. And from the analogy between the polarization states and the spin states of the particle, I am claiming that the corresponding state for the spin of the electron is that when the spin is up along the z direction, these are corresponding to one another and these correspond to one another when the spin is down along the z direction. So this is the first part of the analogy. Now we can also measure this polarization of light along the 45-degree axis. So along the 45-degree axis, so 45 degrees to the x-axis, then the polarization state of the for the electromagnetic wave is given by E naught by square root of 2 I plus j. So this is a situation where the light is polarized in this direction, 45 degrees. Now what is the polarization state orthogonal to this? The polarization state orthogonal to this is this one. Now what is this polarization state? This polarization state, let us call it minus 45 degrees. So minus 45 degrees, and the polarization state So now the polarization state is E naught square root of 2 minus I plus j. Okay. Now in analogy, we can also write down two spin states for the electron which are analogous to this. So let me also write that down. So that is Sx, the situation where Sx has got spin plus. So this is a situation where the x component of the spin is half h cross, and this is and we have Sx minus we have minus Sz, sorry, minus. Now let us see what is the significance of this. So let us analyze this experiment in terms of this. So let us analyze this experiment. The electromagnetic wave is initially in this polarization state. After it comes out of this, it is polarized along the x-axis. So it is in this polarization state. Now if I make a measurement of the polarization along the 45-degree axis, then it goes over to this polarization state, which is electric field polarized along the 45-degree axis. And now if I make a measurement of the y component of the polarization, which is this one, there will be a finite part of this which will go over to this. So I will get some value of the y component of polarization. If I had taken this to start with and measured this y component, I would have got 0. Now what is the analogous situation which we were seeing for the spin particle spin? So now the the spins are randomly oriented. I make a measurement of the z component of the spin. So I can have two possibilities. One is that it is spin up, the other one is it is spin down. Just like the polarization of light, I can have two possibilities. It is either, if I make a measurement of polarization along the x-axis, it will be here. If I make a measurement of polarization along the y-axis, it will be this. Similarly, the particles which come out with spin up are in this state. The particles with spin down are in this state. Now when we take the output from here and we only consider the particles which are in the spin up state, it means that we are only considering this particular state, this particular vector. Think of this as a vector. These are two independent vectors, just like these are two independent vectors. So when the particles come out, this vector represents the particles which come out from the top. This vector represents the particle which come out from the bottom, spin down. We are throwing away this part and we are only retaining this part. Once the particle has come out, now we are measuring the x component of the spin. So if you make a measurement of the x component of the spin, what we get is that the state of the particle will go on to either this or this. Now this vector has this vector as a part of it. Similarly, this vector has this vector as a part of it. So when I make a measurement of this or this, there is a finite chance that I will get this or this. And it is equal because the amplitude of this vector in this or this is the same. Just like if I take a light which is polarized at 45 degrees and make a measurement of the x component of polarization, I will get some amplitude, some intensity. if I make a measurement of the y component, the intensity will be exactly the same, because the components are exactly the same. The light is at 45 degrees. Similarly here, if I take this state, or if I take this state and make a measurement of these two, they will be having equal amplitude. Similarly, if I take this and make a measurement of this or this, it will have equal amplitude. So if I make a measurement of the x component of the spin, when I have made a measurement of the x component of the spin, the resulting thing which comes out will be either this or this. Now if I make a measurement of the z component of the spin again, suppose I take this part, this is the part which has got spin plus along the x-axis. I don't take the particles which have got spin minus along the x-axis. I only take the particles which have got spin up, which I am representing by this vector. I take these particles, and if I make a measurement of the z component of the spin again, which is I make a measurement, so if I make a measurement, if this state over here has some of this vector, has a part of this vector in it, then I will get some particles with spin up. And if this is also there in it, then I will get some particles with spin down. So this explains how, if I make a measurement along of the x-axis and I take the particles with spin up which have got this vector, and then if I make a measurement of the z component of the spin, I again get both these, because both of these vectors are there, because this vector is a linear superposition of both of these vectors, which is exactly analogous to what happens if I make a measurement of polarization at 45 degrees and then measure the y component of the polarization. So in analogy, we say that the particle with spin along the x-axis, with spin plus along the x-axis, can be represented again in terms of these two vectors, just like the polarization of light at 45 degrees can be represented in terms of these vectors. And the particle with spin along the x-axis is this, spin minus along the x-axis is given by this combination of these two vectors. Okay. Now we also have a third possibility. We can also measure the spin of the particle along the y direction. There are three independent directions, x, y and z. Any other direction is a linear superposition of these three directions. So there are three independent directions. So we should be able to make a measurement of the spin of the particle along the y direction also, and that should be independent, some other combination of these vectors. Now how is that achieved? So let us also look at the polarization of light. In the situation where we have the polarization of light, we know that we can get yet another polarization state by so this is the polarization of light. So we have here we have two orthogonal states where the light is polarized along the x-axis or y-axis. We have two equivalent orthogonal states at 45 degrees or minus 45 degrees. Now there is a third possibility where I can superpose these with imaginary coefficients, with complex coefficients. So I can construct a right circularly polarized state which is E naught by square root of 2, and then I have I, the vector I, plus, let me put it here, square root of minus 1 into j, which is I, the number, the square root of minus 1, which is also I. So this is also I, but this I should be distinguished from this unit vector I. Similarly, we have the left circularly polarized light. which is E naught by square root of 2 I minus the square root of minus 1 into j. And these states are two orthogonal states again, and they are distinct from these two different linear states, which the two sets of linear from either this set of linear states or this set of linear states. So this is how we can also represent the spin along the y direction. So a particle with spin y plus is 1 by square root of 2 s z plus I s z minus, and sy minus is 1 by square root of 2 s z plus minus I s z minus. So what have we achieved? We see that the behavior of the spins in this Stern-Gerlach experiments, successive Stern-Gerlach experiments, is exactly the same as the behavior of the polarization of light if you send it through successive polarizers in different directions. And in analogy with this, with the mathematical representation of the polarization of light, any arbitrary polarization state can be expressed in terms of two orthogonal states. So any arbitrary polarization you can express either in terms of light polarized along x direction and one y direction. Equivalently, you could express it in terms of this polarized state and this polarized state. Any arbitrary polarized state can be expressed as a superposition of these two polarized states, or equivalently you could express it as a superposition of the right circular polarized light and the left circular polarized light. Any arbitrary polarization state of light can be represented as a superposition of either these two states or these two states or these two states. So they form a set of basis vectors for the polarized light, for representing the polarization state of light. Either these two, so there are two basis vectors, and you have the freedom of choice of which two basis vectors you want to use, either this or this or this. And any of them can be expressed in terms of each other. And any other polarization state also can be expressed in terms of any one set of basis vectors. And there are only two independent basis vectors to express the polarization state of light. Yes, you have a question?
You are taking the angle at 45 degrees. It can be any angle.
It could be any angle. I could choose any two basis vectors to express it. But this is the one which is convenient, and if I want to draw an analogy with the polarization states, then this is the one which I have to use. Okay, the other combinations will correspond to the spins polarized at some arbitrary angle in between. Okay. So the key feature is that there are only two basis vectors involved here, and any complex superposition of these two will represent a state of polarization of light. And every state of polarization of light can be expressed as a complex superposition of, let us say, these two vectors. Equivalently, we could use either these two. Similarly, for a spin, and this explains all observed properties of the polarization of light, which whatever experiment you do, however many polarizers you pass it through, you can explain it in terms of this. It will go from one combination to another combination to another combination, just the vector will keep on changing. And you can take dot products of vectors and find out what will be the intensity, etc. Similarly, if you want to understand the Stern-Gerlach experiment, then you have to represent it in terms of two basis vectors. And that is it. The outcome of any experiment will be only of two kinds, plus or minus. So you require only two basis vectors, just in analogy with the polarization. one set of basis, possible set of basis vectors is the spin along the z direction. So the basis vectors now are sz plus and sz minus, which is equivalent to saying that for my polarization of light I am going to choose my polarization direction 1x and 1y, and in terms of this I am going to express everything. Similarly here I can express every other polarization, any other spin state in terms of these two states, which are the spin up along the z axis or spin down minus along the z axis. So now if I make a measurement along the x axis, then I will get a spin up along the x axis, and I can represent that in terms of those two states which correspond to the particle being spin up or spin down along the z axis, and that superposition is shown here. Just like a light polarized at 45 degrees can be expressed in terms of Ex and Ey, the particle with spin along the plus x axis, can be expressed in terms of the state of the particle which is along the plus z and the state of the particle along minus z. Similarly, the particle with spin minus along the x axis can also be expressed in this fashion. And the particle with spin along the y axis can also be expressed in terms of this, and the analogy is with the right circularly and left circularly polarized light. And all experiments, all combinations of Stern-Gerlach apparatus which you can construct can be explained in terms of just these vectors and nothing else. So what do we see? We see that in order to explain the spin of the particle, the spin of the electron, the behavior of these measurements on the spin of the electron, you have to introduce some vectors which represent the state of this electron, the spin state of the electron. This is the first thing. And to represent the spin state of the electron, we only need two vectors. It's a two-dimensional vector space, two-dimensional complex vector space, because you can have complex coefficients also. So in this two-dimensional complex vector space, I can have any possible linear combination of these two basis vectors, and each of them correspond to the particle having spin in some particular direction. So this particular superposition, for example, this particular superposition corresponds to the particle having spin along the plus x axis. This corresponds to the particle having spin along the minus x axis. Now if on this particle, say I have a particle with spin along the plus x axis, and I make a measurement of the z component of the spin, then I know what will be the outcome, possible outcome, because this is a superposition of the two z possibilities, two z states. One is spin up, one is spin down. Now suppose I ask you the question that I give you this state, that the particle is in this state. I have made a Stern-Gerlach experiment. Let me discuss this in a little detail. Suppose I send in an unpolarized silver atom through a Stern-Gerlach apparatus along the x-axis, and I will get plus and minus. I disregard the part which comes out with spin minus along the x-axis, and I only keep the part which has got spin plus. Now I send this through a Stern-Gerlach apparatus along the y-axis. There are again two possibilities. It could have either spin up, spin plus, or spin minus. The question I'll ask you is, do we expect to get both of these? If yes, then what fraction of the particles will have spin up, what fraction will have spin down? How will you work this out? It is very simple. You have to proceed just in analogy with the polarization of light. We know that this particle with spin up along the x-axis corresponds to light polarized along the 45-degree axis. So this corresponds to light along the 45-degree axis. This corresponds to right circularly polarized light, and this corresponds to left circularly polarized light. So the question I am asking you is, suppose I have light polarized in this direction, and I send it through a through a device which will only allow the right circularly part to pass through. Will some light come out or not? It is exactly the same thing. How will you do that? You will express this polarization state. You will express mathematically, what do you have to do? Mathematically, you have to express this polarization state in terms of these two polarization states. Any polarization state can be expressed in terms of these two. So you have to express this one in terms of this and this. So let us say we call this ERCP and ELCP. So we have to express this as some alpha ERCP plus some beta ELCP, and any polarization state can be expressed in terms of these. These are just two vectors, and it's a two-dimensional vector space. So I can express it. This is possible. And the coefficient alpha tells me what part of the light will come out with right circularly polarized, what part of the light will be left circularly polarized. So if I send this polarized light polarized at 45 degrees through something which will only allow the right circularly polarized part to come out, then the intensity will be proportional to this alpha squared. And if I send it out through a part which will only allow the left circularly polarized part, then it will be proportional to this beta squared. That is all. Just the Malus's law, in something like the Malus's law which you have in polarization. So similarly, if I send this through something which will only allow which will measure the y component of the spin, and I ask you the question, what fractions of the particle will come up with positive spin along the y-axis, what I have to do is I have to express the particle is initially in the state with spin plus along the x-axis. So the particle is initially represented by this vector, spin plus along the x-axis. I have to represent this vector as a superposition of these two vectors, which is possible, not difficult. And the coefficient of that expansion will have two coefficients. One will be, so this vector will be some alpha into this vector plus beta into this vector. And the fraction of the particles which will come out here along with spin plus along the y-axis will be the coefficient of this vector in this expansion. And the particles which will come out with spin minus will be the coefficient of this in this expansion. It is exactly analogous to the polarization. So what do we see? We see that the states of particles have to be represented. If you want to understand the quantum behavior, you have to represent the states of particles by vectors. And these vectors it's a complex vector space. So any linear superposition of these vectors with complex coefficients is also a state of the particle. This is the second thing. So I shall elaborate on this in the next lecture. Before ending, let me tell you something very interesting about two-state systems. Let us say about the polarization of light. Any arbitrary polarization state of light of polarized light can be expressed in this form. So the light is traveling along the z-axis. So if I take E naught E, which is a function of z and t, is equal to some E naught C1 into I plus C2 into j into e to the power I kz minus omega t. Please remember that this e to the power I kz minus omega t appears throughout. I have not shown it explicitly. Now, any arbitrary polarization can be represented in terms of two complex numbers, C1 and C2. So I will not bother about putting the rest of this thing anymore. I shall just deal with these two complex numbers, C1 and C2. They represent the polarization. So any arbitrary polarization can be represented in terms of C1 and C2. So polarization along the x-axis, this is C2 equal to 0. Y-axis is C1 equal to 0. Polarization at 45 degrees is C1 equal to C2. Now in this way of representing the polarization state, the overall amplitude, I could multiply it by some number A and it would still be the same polarization state, just that the intensity would have changed. So I don't have to bother about the overall amplitude. So instead of using this whole, instead of using two complex numbers, so I can use only one complex number, and that can be achieved as follows. I can divide throughout by, let us say, C1. So if I divide throughout by C1, then I have 1 and C2 by C1, and I can take the C1 outside. This equivalently represents the polarization state of light, or you may say the spin state of a spin half particle. They're exactly the same mathematically. So I have to only now bother about this one complex number, let us call it 1 and z. This tells me the polarization state of light, because this C2 by C1 is one complex number. I am not bothered about the amplitude. Now what are the various possibilities? So if z is 0, this is light polarized along x-axis. If z is infinity, then this is light polarized along y-axis, because C1 now is 0 and C2 by C1 is infinity. So if Cz is infinity, then this corresponds to light polarized along the y-axis. If z is equal to 1, this is light polarized at 45 degrees. Z equal to -1 is minus 45 degrees to the xy axis. Similarly, if z is equal to I, then this is right circularly polarized. If z is equal to -I, this is left circularly polarized light. So now we see that one complex number can represent the polarization state of light. If I just tell you one complex number, you can tell me what is the polarization state of light. Any elliptically polarized light can also be expressed by just this complex number, because elliptically polarized light will be just arbitrary. See that the imaginary, if z is purely imaginary, it is circular. If z is purely real, it is linear. If z is some arbitrary complex number, then it is going to be elliptically polarized light. Okay. Now the question arises, how can we nicely represent complex numbers? Now complex numbers can be represented in a plane. So if I have this plane, let me draw the plane like this for reasons which will become clear shortly, xy plane, and any complex number z is equal to x plus iy. So the origin okay, so the origin over here is light polarized along the x-axis, because z equal to 0 is light polarized along the x-axis. The circle at infinity corresponds to light polarized along the y-axis. Things along the x-axis correspond to which is real, correspond to linearly polarized light, and everything else is circularly polarized light. Different states of circularly polarized light. Now so this is one representation, but the representation, there is a neater possible representation, that is through a sphere. So suppose I take a unit sphere. So I take the unit sphere 1, I draw a unit sphere which is known as a Poincare sphere. So let us consider a unit sphere, and every complex number can be represented as a point on a unit sphere by just projecting. So if I want to represent this complex number, what I do is I draw a line starting from the north pole and coming to this point. Let us say this point here on the complex plane. So this line will intersect this unit sphere at one point, and that point will represent this particular complex number. So if I want to represent the origin, then I have to draw a line starting from here going straight down. It will intersect the unit sphere at the south pole. So the south pole corresponds to this point over here. If I want to represent the infinity, I have to draw a line which intersects this plane at infinity, which is the line like this. So this point represents the whole of infinity. So you see, the polarization states of light are actually not the full complex plane, but all the points on the complex plane with all the points at infinity identified with one point, because all the points at infinity represent only one polarization state. And here also we see that all the points at infinity correspond to this point over here, because the line passing through this point, cutting this plane at infinity, is this parallel line, and this intersects this plane at infinity. So if I want to intersect infinity at this side, then it will be this line. All of these lines are tangential to the circle at this point. So this is the point which represents infinity. So whole of infinity is represented by this point. And let us say this point over here. So if I want to find out which point on the plane this point represents, I can just extend this and I will get this here. So the whole of the southern hemisphere represents things which lie within the unit circle. That is quite obvious, because this is the xy. Let me draw it again. This is the unit circle in the xy plane. And let us look at the sphere. If I take a line starting from here, so if I want to, let us say, find out the point on the sphere corresponding to this point, I have to draw a line like this. So everything which lies inside the unit circle will have the corresponding points on the sphere in the southern hemisphere, and all the points in the northern hemisphere are points which lie beyond the unit circle. Okay, so all polarization states of light can be expressed by points on a sphere, and this sphere is called the Poincare sphere. Similarly, all states of a spin half particle can be constructed by superposing Sz plus Sz minus. So there are two complex numbers, and it is only the relative phase between these two, the ratio of these two, C1 and C2, which determine because an overall number over here, I can multiply the whole thing by alpha, some A, it will not change anything, because after all, finally I will want to normalize it, make it a unit vector. So it is just the ratio of these two numbers which is going to determine the spin state, and any spin state of the particle can be represented by one complex number with the circle at infinity identified to one point, or any state of the spin half particle can be represented by a point on a sphere. And corresponding to every polarization state of light, there is a unique spin state of a spin half particle, and vice versa. There is exactly a one-to-one mapping between these two. And this is something which is quite deep and quite very significant, but we shall not pursue this anymore. We shall now go on to discuss the structure of this vector space and other such mathematical details in the next class.